Hi, I'm Davor from the University of Zagreb School of Medicine, Department of Pharmacology, and in this video I will show you how to assemble your friend MIROSLAV, the Multicage infrared open source locomotor activity evaluator. So let's get started. Okay, so once you've gathered all of your parts, we can start with the printed circuit boards and take a look at what we have. You will likely get them in this panelized shape with a lot of boards. You'll have a lot of spare ones probably. Then you can just easily pop one off as needed. Now, we have four main boards, four main designs that we use in MIROSLAV construction. It's these four. So, this is the power board, which is pretty simple. You basically just have your power jack, which you will place like so, and then you will solder it down, followed by all of the different connectors, which will connect most of them directly to MIROSLAV cage units, like this one. And one of them will also connect to power the main board. The main board will then in turn power the input serialization board. And finally, this is the PCB that you've just seen assembled here on top of each MIROSLAV cage unit. So these boards are generally pretty simple, and we're kind of banking on the fact that we have a development board here that's doing most of our work for us. So I'll explain this in a bit. So let's get started. Now here I'm kind of assuming that you started off like we did, or like I did with the first prototypes of MIROSLAV, where they were kind of simple and mostly proof of concept, and now you want to make something that's a bit more robust, a bit more high throughput, and that was the idea behind the creation of MIROSLAV. So at this point I won't really go into all of the tiny details like how to solder. There are a lot of excellent guides out there on it, and it's likely that you can already do it, or you know someone who can. But there's levels to soldering, and with this in mind, most of the components for MIROSLAV were designed, solderable components, are actually through hole and should be fairly easy to solder. So, for example, all of the connectors, let's start with the simplest board. So, it just has a barrel jack and a lot of these 2-pin connectors. One pin is for plus, 5 volts positive, and the other is for ground. We'll be using plenty of them. And as you can see, basically on all of the boards we're mostly using these 2-pin connectors, and sometimes where we needed a 4-pin connector here, which are these ones, to minimize the number of different connectors that you need to source. With these boards, and we've actually done this, these power boards are kind of meant for you to design your own, depending on the power supply that you have. For instance, with these particular boards, in the end, we mostly used boards where we didn't populate all of the connectors. We populated about half and connected one power supply, like this one, to the board. And then we connected another supply to the second one. and another to the third one. Depending on the number of sensors you have, this was done to distribute the power load and kind of have more weaker power supplies instead of one big one. So this is an approach you can take. So I'll just stick a few connectors, flip the board around. Now they're all mostly in place. And I can go on with the soldering job. Might zoom in so you can see better what's going on here. It's good to know that for the power board you will have to apply heat for some time, because as you can see, all of this green part, you can see that it's a bit darker green in here. That means all of this is copper, which will act as a heat sink, meaning that it kind of draws away heat from the pad, making it a bit difficult to solder. So if you just keep holding on, let's try a bit more flux. We have plenty of solder, too much actually. And all of this acting like heat sink is why I am using so much solder, because it does kind of make it easier. Alright, that's it. Yeah, it's not going to be perfectly aligned unless you're really careful about it, but if it works, it works. For this it's quite alright. No. Another big one. This now holds it in place. Again, too much solder, strictly speaking. This one's a lot better. And again, too much solder. But that's it. And again, feel free to populate as many or as few as you want. So let's take a look now at the cage mounted sensor array. This is what goes on top of the cages, screws to the lid with these wing nuts. The PCB electrically is pretty simple. So the RJ9 connector goes to the top, and on the bottom the standard 254mm pitch headers, like the one you would see on an Arduino Uno. These headers you can get, these are specifically made to be 4 pins. I don't have 3-pin ones, so what's commonly being sold is these 40 pin ones. So to turn these into a 3-pin, you just cut them. So first I'll pull out the contact after I count out 3 pins. And then I'll use a pair of snips to cut it. And it just kind of popped. It's not the prettiest variant, and we can trim this out, but it's pretty okay. Now let's get another one. There it is. It's important that all of the 3 boxes which will actually have the contacts are intact. We don't really care about the plastic flaps that are left over on each side. So let's solder this. Note that these 2 go on the bottom, because that's where the sensors will be. You could help yourself by using some helping hands, like those alligator clips that hold everything in place. Now first I'm just soldering 1 pin on each side, so that the whole thing remains in place. There it is. Now I can check. And yes, it's pretty nicely leveled. If I were to solder everything and notice that it's kind of shifted, I would need to rework the entire thing. This way I can just heat up the 1 pin, realign it, and that's it. If you really mess up, you've seen how easily the contacts go out. You can do the same vice versa. So just take a pair of pliers and pull this off. Then you'll have individual contacts which are much easier to desolder. These things are cheap, so you can do a number of tries. Now let's solder around the rest of the contacts. And again, the square pin will be a bit of a problem because it's the ground pin. It's connected to the entire ground plane, which is basically a copper plate and not a thin little trace like the other contacts. So it acts as a heatsink and takes a while for it to heat up. Essentially, yes. Alright, so it is. Now let's add the RJ9 connector. What I really like about this one is that once you align it, it pops in and it's held in place. And now you can just solder the individual contacts. Be sure it's seated properly, and let's do it. That's it. And that's the board. We'll set this aside and I'll tell you more about how this comes together into this later on, once we've finished assembling all of the PCBs. Okay, now let's move on to the main board, which is this one. And its main component is actually not a single integrated circuit or something like that. It's this entire dev board, which takes care of a lot of hard work for us. This is actually composed of a few components, like a voltage regulator, which we'll come back to in a bit, USB bridge, which enables USB communication, so you can plug this into your computer and upload code. And actually this is again a module which contains the microcontroller, its SPI memory and everything in here soldered on top of here. And then it has these, it's made for much smaller systems, and then it has these easy to access pins. Now you have 2 options. You can actually take this, be careful not to flip it the wrong way. This is your hint. this stuff, these lines, signify this antenna protruding from the board. So this is the correct orientation. You have two options. You can take this and place it into the board, like so, and solder it permanently. Or you can actually take the headers, cut them to the appropriate length, number of pins, and solder them in there. However, before you do this, I recommend that you take care of these two little guys. These two are needed for appropriate I2C bus functioning. We will use this connector to connect to the daughter board serialization stack. And why I'm suggesting that you solder these first, it's because all of these other components are fairly tall. I have an assembled board here where I can show you. Here are the headers, on top of which this is plugged in basically, and all of the connectors. To access these two little resistors and solder them down, it's kind of difficult once you already have all of this in place. So it's best to do this first. Now, this is the part of soldering that's a bit more difficult. The good news is that these are very, very common parts. You would use 4.7 kilo ohm resistors, and if you're ordering them from a manufacturer like GLC PCB, as I did, they also offer PCBA service, PCB assembly. So you can order these simple parts from them and have them pre-solder them on top of the board for you. They might also have these connectors in stock, though I'm not sure if they do this for through-hole parts as well. They might actually do it for the daughter board chip, but it's most useful and definitely available for these SMD components, which are a bit more difficult to solder than the through-hole components. However, we've used the 1206 format, which is pretty big and shouldn't be a problem, provided that you apply the proper technique. So, I mean, there is no one appropriate technique, there are many, but what I like to do is what I'll show you in a bit. So you can see these small resistors here, they're over here, and what I do is, actually I don't immediately pick them up. First, I'll wipe down my soldering iron to get rid of excess solder, because I only want a bit. And this solder wire is a bit too thick. I will probably lay on too much solder at first. And that's it. So I just put in a very, very small blob of solder here. Now, if you have flux that goes on the board, feel free to apply it very liberally here. Otherwise, I will jab my soldering iron into here, take one of these resistors with a pair of tweezers, and of course wipe off the excess solder first, reapply the flux, and then I will reheat this little blob and push the resistor into it. There it is. There's a bit too much solder on here, but it's important that it's being held into place. You can see that it's kind of blobby, so we will reflow this, but the important thing is that this way it's kept in place, so you can solder the other end properly, and then we'll reflow the first one again. Generally with soldering, just a quick tip if you're struggling, the main rule is to try to heat up both surfaces at the same time. So you're joining two parts, you want to apply heat to both of them. Since the tip is a piece of metal, you cannot really get good contact area with two pieces of metal which are just kind of points touching. So if you apply some solder to the tip of your soldering iron, at these temperatures it becomes soft, and then it's not just two firm metal pieces coming into contact. It's one firm metal piece and a blob of metal which can kind of press itself onto the other contact and transfer heat much more efficiently. So this is why I kind of add a bit of solder onto here. Try to touch both sides, both the resistor and the pad. And this would be easier to do with thinner wire, otherwise I will probably be adding too much solder again. And that's it. And this is a comparatively this is a nicer connection, though it is a bit too much solder. I keep saying this because this is what you will see in examples and good soldering practice tutorials. However, it's the main disadvantage of too much solder is that you cannot really evaluate well, especially in through-hole parts, for cold joints. Otherwise, if you take care that you've applied enough heat and that everything is actually, you're sure that it's soldered well and that you've applied enough heat and solder has passed on to both contacts, this isn't actually a problem. It's just that it's difficult to evaluate whether you've managed to do so or not. Now I'll reflow this other side again. Sorry. And now it does look a bit better, though still a bit blobby. Let me try it again with the other part. I can flip my iron. And maybe I'll be able to put in less solder. Let's try it out. Okay, by the shine you can already see that the left one is flat and the right one has a bit of solder on it. So just a little. Let's see how this works. That's a nice big drop of flux. Generally you would use isopropyl alcohol for this. You can burn it off though, just so I can get a look at the joint. It seems okay for now. As I said, it's important that it's keeping the resistor in place while we solder the other joint. Not gonna fiddle around with it too much. It's good. It's been good for some time, but sometimes it's good to play around with it so you see how everything behaves. And I haven't done SMD soldering in quite a while, even these big parts. It's fun. Okay, now the other stuff you would just populate it as we did. A new thing that we're using are these vertical 4-pin connectors. Let me just show you how it looks. The good thing about these connectors is that they're polarized. So you see this notch, the other end, Let me just see if I have one of those here. Yep, I do. So you cannot physically jam it in like so. Because of the notch, it only goes one way in. I mean, this is quite common, but it's good that you don't have to worry about this. Which is actually not the case, for example, with these that you've seen. They don't have, this is so-called keying, so they're versatile, but yeah, for some more well-defined stuff, this works better. So this is the new one. It would go here, like so, and in these two parts again. Okay, I have a board that's already soldered and completely populated, and I want to talk about it a bit. So let me just put in the dev board in here, so you can see what it looks like when it's actually generally ready to be used. So this is actually the version 0.4, which is what we've done our experiments with, but we've since revised it into version 0.5, which is on the GitHub repo. The designs are there, but we haven't actually tried it out. We haven't built new 0.5 MIROSLAVs, and it's just modifications based on some stuff, some fairly minor stuff that we've seen that's kind of an inconvenience. For example, you can see that this doesn't really look that great, and the reason is, well, because while I was designing this, I wasn't thinking very well. So these two boards, first, they're too close together. I wasn't counting on the board being so wide to the left and to the right of the connector. But the good thing is, you can see when with the lighting hitting it just right, that there are no traces here. So I was actually able to just cut off the side of this board with no consequence to its operation. For these two, I would also use these headers. However, if I were to do so, these pins would likely be touching the USB connector, which is protruding from the board just a bit. So I didn't want to risk it, and as these are fairly cheap, I soldered them down permanently. In the new board revision, we expanded the board a bit and we moved it here to the side. When mounting the board, for example, you can mount it to the wall or in an enclosure or something like that. I'm not sure if this has a big effect, but it might be good to mount it, the new version, which I hope you'll be using, that you mount it here so that the environmental sensors, which are these two, are here. Again, I'm not sure if this has a big impact, but the main chip might heat up a bit. So my thinking is that it would be good to have it go upwards. So if this is up, if it's mounted like this, warm air will go there and not over the sensors. For example, as it would if I were to mount this board like so, or the other board like so. If the sensors are here, hot air might mess around with the readings. It might not, I'm not sure, but might be good to keep in mind. The other thing that's different between this version 0.4 and version 0.5 is that these boards are actually ESP32S2 Saula 1 boards, and these boards aren't in production anymore. They were superseded by the ESP32 dev kit boards, and it's corrected in the bill of materials as well. So the dev kit boards are available, can be bought, and they're very similar to this one. They also have the ESP32S2 module, and they work just as well, but it did require a board revision. So generally it will be some convenient stuff, like you don't have to muck around with how you mount these sensors. There are mounting holes, so you can affix this board with screws to something and not just double-sided sticky tape like I used. And you will have an easier time getting the dev kit than you will to get the Saula, which was in production and was recommended for new designs back when the version 0.4 was designed. It's not recommended for new designs anymore. We will now leave this to the side for now and look at the dreaded input serialization board. It has one of these pesky SMD components, which is a decoupling capacitor, and I actually have a number of soldered boards where by accident, I was under time pressure, and by accident I missed this capacitor from my order. Luckily, I did have these through-hole capacitors that I managed to solder onto the surface. So you kind of make do with what you've got. Regarding the connectors, these you will generally want to populate all of them, as these are the ones that will give you your cage functionality. The cages connect the output of the cages, the data in connects to each of these contacts. Then this integrated circuit pulls all of these connections into a serial bus like USB, the universal serial bus, but this one is I2C, inter-integrated circuit connectivity. Now this board doesn't have the I2C connector. This one does. It's also missing this 3.3 volt in connector. This is the power connector. So data in, power in. Why? Because it has these two connectors. And you can actually also see the traces. They're going from this connector to this one. These traces are going from this connector to this one. Why is it organized as such? Because it's meant to be stackable. This is meant to be the topmost board. So it will have, all of them will have their own slew of cage connectors, but only if you're using just one, only this one will have will be populated with the connectors, and if you're using more, you will then also solder these headers to the bottom. These are so-called female headers. There's a 4-pin one and a 2-pin one. You can put them in a line as well. I stagger them to maybe just get a bit more structural integrity, though you really shouldn't be relying on this. That's why these have mounting holes from the start. The idea is that you will have a screw keeping all in place, which I'll show you in a bit. And then we have one that's the middle one. So you can see that these, why am I saying that you can stagger them? Because it doesn't matter if you put this into the right series of the 4 holes or into the left series. Similarly, it doesn't matter if you put these two here or here. So again, these two are the power, these 4 are the I2C bus. It only matters that you get it right on your next board. This is why this is done, because of the middle boards. So these connect to these two, and now if you want to pipe this down to the next board, you have to use the other pair of holes. So this is why they're kind of alternating. Once you press them together, it works like this, and then the bottommost board works like this. if I wanted to, I would solder pins, the female header, so these ones, I would cut them into 2 and 4. I would solder it here, so they point down, and then I could attach another board like so. It's generally a good idea to use females on the bottom and male pins on the top, simply because if this board is connected and energized and the stack is designed so that the main connections are on the topmost board and then they're optionally propagated to the bottom ones, it's good to have them be female headers, because if you, for example, decide to use this board in a setup which now doesn't have any more boards, so for example I'm using the stack like so with 3 boards. A couple of months later I have another experiment and I really don't need these 2 boards. I only have 8 cages and I'm satisfied with having 1 board. These are shrouded, whereas these are bare contacts. So you don't want energized bare contacts just protruding on the other side of the board. So you would put the female ones in the device that's giving the power and bus contacts, and this one would receive them with the male pin headers. So why does this work? Well, because this, in terms of power, this is parallel connection. Power goes here, from here it goes to the GPIO multiplexer. That's how they're called, because this is just a general purpose input in this case, which takes in TTL logic, transistor to transistor logic, to read the 0 or 1 levels from the peers, and then translates them into I2C messages. So the main board will connect to here. As I said, power goes from the connector down to the other boards, and within each board to the chip. Data, on the other hand, goes through this connector to this chip and propagates to each of the boards. So a good thing about buses is that you can have multiple devices on them. In this case, each one will be on the same bus. So that's why these 4 pins can just propagate down, and you only have 1 connection for the entire input serialization stack. So how does the main board differentiate them? That's where the last, second to last part of the board comes into play. It's the little address pads. Now these aren't actually pads for SMD components like we had before. These are pads that you can apply solder to determine the address. You will see in the Arduino code you can put in the address for the topmost board and all of the other boards in the input serialization stack. So in here the topmost board has the address of 100. You read it by seeing, let me just show you the bare board. You read it by connecting the middle pad, just bridging it with solder to the left one or to the right one. If you bridge it to the left one, address bit 1 will be 1. If you bridge it to the right one, address 1 will be 0. This is what you will input into the Arduino code, so that the main board knows how to transmit, which devices to look for at which addresses, and how to align the messages. This you will then use in the other Python scripts of the Slav package, like preparaslav, tidyslav, etc., to assign cage numbers to all of these different inputs. If you mess this up, you will actually mess up the order in which data is sent, and it will be difficult to tell which of these boards corresponds to which line of bits in the data. And again, like I told you, this isn't really robust. It would be prone to breakage, so I'll disconnect the boards in this stack. And I'll show you a setup with the mounting holes, where the mounting holes are actually being used. Now, this is just a cheap plastic container which we drilled holes into and put in zip ties. So this plastic container is zip tied to, let me just zoom out a bit. It's zip tied to the side of the cage it's zip tied to the side of a rack. This kind of gives it a bit of dust protection, though not a lot, because we cannot really seal this, as many cables will come from all of these connectors to the cages. But it was a nice, quick and dirty way to mount it to the side of the rack. Alright, so to get a closer look here, we can actually unscrew this. Kind of tended to use wing nuts everywhere, because you don't actually need tools to at least disassemble the big stuff. Okay, so what we did here was make this stack kind of robust. You can see that it doesn't really move. It's fairly solid because of this arrangement of screws. So what we did was basically take a serialization board. We put a screw in there, and then we used this little type of plate, which you can see that it's cut. I mean, you're probably familiar with this stuff already. We would slide it onto here and then screw down the nut all the way down. Now, don't worry, I won't be assembling the whole thing. Now, while assembling it, I left this loose, and then I put in another nut, which is kind of a delimiter, because then we repeat the process. Once we put in this nut, put in the next board, and screw this onto here, this is kind of a sandwich, which keeps the middle board firmly in place. So the top nut is kind of a delimiter, and the bottom nut is what affixes it. And similarly here. At the end, we use the wing nut to affix this to that container that you've seen before. Now, why did I mention that you kind of don't want to tighten all of these nuts immediately? Well, because if you do, if you tighten this screw right now, put in the second one, third one, fourth one, it's likely that they won't all be perfectly straight, and you won't be able to put the middle board on top of it and then the bottom board. So I keep it loose until I position all of the nuts in series and all of the boards in between, And then I use a pair of needle nose pliers. I can grab the nut and tighten it. A better option, a bit better option, would be to use these nuts here. Let me just remove this. For the cage sensor arrays, it was really important that they all be at the same height, and that this is pretty fixed. Kind of the same case. You're delimiting with the nut how far this can go. So what we use here is this special nut that actually has this rubber band, rubber seal, or rubber O-ring in here, and you cannot unscrew. You've seen how easily the nuts go. You cannot unscrew this with your hand. You really, well, maybe a bit. It's difficult. I really couldn't do this with just my fingers. You could use this here, because if you're tightening this, then this top nut kind of wants to move a bit with the nuts, with the O-rings, with the stoppers. They will kind of pretty much be in place. But what's even better is if you find the tall nuts. I'll put in an image. As you can see, tall nuts like the one in the image, that would basically be just the right height, where you would just screw them onto here, put the board, screw one here, and that's it. You wouldn't have to fiddle around with adjusting the spacing. All things considered, I thought it was a minor inconvenience to pay for the convenience of being able to have a modular input board serialization stack with 1 to 8 boards, however many you'd like. Okay, so now we've started talking about the connections. Let's go now from the input serialization stack to the main board. Now, the only thing I've mentioned with the power board was that you would likely be using one of these to power the main board. Now, this one has two connectors, S board and board, but ultimately this board ended up being 3.3 volt powered. Why is this important? Because you want to power the entire thing. Well, not necessarily the entire thing, but you want your heftiest power supply to be 5 volts, because the peer sensors, which you will have a lot of, will take in 5 volts. They're perfectly happy to send out a 3.3 volt signal, but they are powered with 5 volts. This works well because even though these chips, all of these dark ones here, the MCP2317s and the ESP32s, they operate at 3.3 volts. But why is this not a problem? As I told you, this is actually a dev board which has all of these nifty features. The LED we're not using, but here comes the voltage regulator that I mentioned. It turns 5 volts either from USB or from here, from the 5 volt in, to 3.3 volts to supply this one, this chip, the actual ESP32S2. And this, the 3.3 volt output, is broken out to this pin right here, the first one. You can see 3V3. It's a way of putting a decimal point in there. So this is 3.3 volts. And of course, the point of MIROSLAV wasn't just to make it for our own use, it was to make it modular. So there's also 3.3 volt in here. So you can power this board on its own from a 5 volt power supply or from a 3 volt power supply. In our setup, we use the 5 volt power supply, where we just used one of these connectors from the power supply board. to the 5 volts in. Be sure not to put in 5 volts into here. If you put 3 volts into 5 volts, it just won't work. But if you put 5 volts into the 3.3 volt in, you will fry this little guy. And that's where having it be replaceable comes in handy. This is like 7, maybe 10 euros, and it saves you a lot of time to not have to solder all of this again. You just pop this one off, put in a new one, and that's it. So this provides 5 volts here, and as I told you, the power board supplies 5 volts to the cage sensor arrays, as in the schematic in the paper. Okay, I've disconnected this so it doesn't flap around, but once this is powered with 5 volts in, this entire board is energized, so is the voltage regulator, and it can give some power to the 3.3 volt out. You cannot draw a lot of power, but luckily these MCP chips don't. And I told you that power propagates down the entire stack. So to power this stack, as these are 3.3 volt chips, you cannot power them directly from the power board, but you can simply connect them to 3.3 volt out. And the cable connects to here. As I mentioned, this on this end is the 3.3 volt in. It's the power supply. Okay, so you connect the power to the input board serialization stack, and you connect the messaging, the I2C, like so. And again, now the entire stack is actually connected via these connectors down here in the middle. Just as a brief aside, these connectors labeled int, they're actually the interrupt pins of the MCP 23017s. This means that when a pin change happens, state change happens on some of its outputs, it can produce a state change on the interrupt pin to let you know that something is going on here. In our MIROSLAV setup, we're continuously monitoring all of this stuff, so we're not using it. Again, it was built to have flexible, wide functionality, and that's why this int thing is here, as it might be useful to someone who's using a MIROSLAV. Now the ENV peer is also a peer sensor with it's all kind of makeshift. On this side it has this it's taped down, because this was actually the peer that we've used in the habitat. So it has this reversible connector where you have to be careful how to connect it. I wired it so that the metal part, which is not visible here, it's visible here, that it points inwards. This kind of made it easier for me to remember. And it goes down to one of these connectors. Let it focus, that's it. So you can see how this needs to be wired according to the schematic. And this goes into here. This ENV peer is the passive infrared sensor for the environment. This peer was actually taped to the rack, and it monitored personnel entrances into the habitat. And the last connector is one that we haven't used, but you can. And I mean, I think it's a nice thing to have. It's the I2C bus. This little thing has two of them. The second one is connected to these two sensors, which we deem the most useful. One is a temperature sensor, and a humidity sensor all in one, and the other is a light sensor, illumination sensor. So MIROSLAV comes equipped to take on these two sensors, but if you need more or if you want different sensors than this one, you can connect them to here. You can also design an entire board of your own, which has an I2C interface sensors that connect to here. And let's take a look at the cage sensor arrays. These are the ones that you will be busiest with, because probably you will need many more of these than you will these, because one MIROSLAV will be connected to many of these. So let me just find the board. Here it is, the newly soldered one. This board is devised to have a different connector than these ones that the peers usually have, that I've showed to you with the environmental monitoring peer for human entrances. So this is what a peer module looks like. It's an HCSR501 module, and it can be bought for pretty cheap from hobbyist stores. Just a note about these modules. They have these potentiometers, and it's described in the paper how they trigger. So once they detect movement, they go from logical 0 to a logical 1, they hold it for some time, and then they go back to a 0, which they hold for some time. How long they hold the 1 is determined by this potentiometer, and the other is for sensitivity. You can see in this picture what's for what. And like I told you, it holds a 1 for some time, but this jumper determines if this time is fixed or if this time is extended by continuous movement. It totally depends on you how you will set it up. We set it up for retriggering, where extended movement will re-trigger the sensor. As soon as it stops detecting movement, it will go to a logical 0 for some time. It's about a second. It's in the documentation, which is linked down below in the description. A very important note about these sensors is that they come from the factory with variable sensitivities. Now, this wasn't a problem at all for us, because we were interested in treatment effects of streptozotocin and later on of different drugs that we tried out, which we wanted to see if they would have an impact. So we were interested in changes from baseline. So that's why we simply employed a standardization of each sensor to its own baseline measurements. Basically, if you don't have a baseline, these are pretty much useless. But what you can do is use sensors that aren't hobbyists, that are professional industrial sensors. Panasonic makes some which was used in another peer-based system, the Compass, and that one is kind of a fully integrated plastic little thing with just 3 legs. So these boards could easily be reworked to work with those sensors. You would just modify the layout in KiCad so that these 3 pins don't go to here, but go to somewhere in here. As in the image, you would find the footprint, and you would design the PCB accordingly so that they would just kind of plug into here, solder on this side, and come on top of the cage onto some type of carrier, which is what we have here. So why am I even talking about these modules in the image? You can see that they don't have adjustment pins because they're factory calibrated. So basically they do measure, each sensor measures in a way that's comparable to other sensors without correcting for some baseline. This is very useful, and this overcomes a pretty big limitation of this type of system if you need it. If you need it, you will need to spend not €1 on each of these sensors, but about €20 on each of these Panasonic industrial sensors. So it's kind of a trade-off. Since we're interested in differences from baseline in our study design, this made a lot more sense. If you want to measure locomotor activity of animals that haven't been treated and you're not interested in differences but actual absolute activity that's comparable, then by all means you need to get the Panasonic sensors. Okay, now we have the one pair. Let's grab another one. The way that they're connected is like so. One's here, the other one goes here. You can, after this, you kind of want to have a way to affix this entire thing to a cage. And the idea was to make it as simple as possible, which was to actually just have a long screw that would go through here, and then it would be screwed to the top of the cage, like you can see here. So these are actually two wide little plates. The cage lid would come in between this. You would grab this cage sensor rail like this, put it on the cage lid, and you would apply from the bottom. If the cage lid is here, you would put this, screw it with wing nuts, and you would do the same for the other one too. This is part of MIROSLAV, which you will probably want to modify, especially because a lot of people have 3D printers by now, and you probably want to save yourself some time by actually 3D printing this stuff instead of building it by hand as we did. So what we did here to get from this to this was actually we took a cable raceway, we cut it down to these lengths using a table saw, and usually it has little hooks here that we sawed off, little hooks that take on a lid, and you can actually see these hooks here, the other side of these hooks. Why? Because these are from the lid. So we cut the raceway into this length, we cut the lid into this length, and then we just glued pieces of the lid to the sides to close it off. As for the holes, the diameter, these spacings, all of this, these two holes, just by the way, don't mind these two holes, the wide ones on the top and the bottom. These are actually part of the cable raceway and not holes that have anything to do with making a cage sensor array. So all of these dimensions are can be found easily in the PCB files for this PCB, for this one. But you can actually also measure it by hand, because that's why we put in these lines and this little square. As you can see, the diameter of the lens, which is the diameter of the hole you need to drill into, or the hole you need to put into whatever you'll be using, the diameter is about the same as the width of the sensor, which is about the same as the distance between these two lines, these two. So that's the diameter of this hole. It's centered to these smaller holes, which are M3 for 3mm screws, and this the hole on this side looks weird because it's just to give you kind of a little space if you miss a bit with the alignment, that you have a bit more space to actually you don't have to be as accurate in your drilling if one of these holes is oval and not circular. So, oh, and one more thing, there's this little label, bottle label, so as they come on top of the cage, usually this is where the bottle would be, and this helped us to not miss the orientation when putting these cage sensor arrays, so they were all oriented the same. Okay, so why this entire white thing then altogether? Well, because first of all, it's kind of a base for the piers. It's a base so that they don't wobble around. We simply used hot glue to hot glue them into place like so. After that, to kind of have everything together, we used a similar principle as in the daughter board stack, which is here. You can see a similar principle of using nuts to sandwich something at some point of at some length. Like, imagine this white part is the middle board here. You can see how these two nuts are sandwiching it into place, which is exactly what they're doing to the white enclosure here. Here and here. We have these the sliced little plates here and here. This keeps everything in place, and these aren't screwed together. The screws aren't affixed with nuts here because they're just the screw is actually kind of pressing down on this PCB, not a lot, just a little, and presses the PCB onto the piers. So it's kind of it's in my opinion a really elegant solution that Jan and Anna came up with. I can take no credit for laying it out like this. And the purpose of this is not just to serve as a base for the piers, it's also to serve as a collimator. Basically, these little piers have nearly a 180-degree field of view in this entire plane. So both the size of this height, well, this height is mostly determined by the actual cable raceway that you get. The width, you just buy the raceway in the width that you want, but then you can vary the raceway's height, or not really the raceway's height, but how on the cage lid, how tall the pier is. You want it to be low enough so you don't have line of sight. Let me explain what I mean. Let's actually affix this properly. So the way we've always mounted it, we always put our bottles here on this side, and then we orient this so it points to the bottle, which is at the part farther away. So I grab the plates like so, put them. I actually would count which hole I'm putting it in, and then I would align it with this line here. Now I'm not doing the counting, but yeah, because this is not the experiment. but yeah, I did. And then I would take one plate and one wing nut. Flip this around, being careful not to drop it. Put the plate here. Screw down. Alright, here we go. If this is the top of the cage, and here's where the cage starts. If you drop down and try to take a look, you shouldn't be able to have a direct line of sight to the sensors, except through the cage. Why? Here they are. Why? Because if you have line of sight through the cage, that means the only way the sensors can see you is through the plastic cage. And the infrared doesn't pass very well through the cage, and we haven't been able to trigger these sensors with any movement outside of the cage. On the other hand, if you didn't have this, if you just had like bare peers like so, if you walked in front of it, would pick up stuff from within the cage, but if you walked in front of this, it would pick up your movements as well, which you do not want. So this is the purpose of the white thing as a collimator. You can see from all angles, as you tilt it, you cannot get a line of sight to the piers from outside of the cage. An excellent question that a reviewer had was whether there are any dead zones. We actually put in a video on a repository of a test MIROSLAV setup that we tried out exactly to map the animal's movements and position to the reaction of the peers. So it's a modified cage sensor array. It does have a bit different collimator, but the lines of sight should be approximately the same. The difference is, in that video, it has two LEDs, one for one peer and the other for the other one. There's two videos, one from this side, one from that side, and both are recorded simultaneously, and you can see both of the LEDs in the shot of each camera. One is set to low sensitivity and the other is set to high sensitivity. If I recall correctly, the green one is high sensitivity, and this shows you peers of two different sensitivities with this potentiometer configured and how they respond to animal movements. And while there seems to be a bit of a dead zone in the cage down below, it's pretty much if the animal is standing here, and you can see that if the animal is moving its head here and there's food here, that there is no line of sight to the cage array. However, the body is here and it does have a line of sight to the cage array. So if the animal moves here, it's generally captured, but if the head moves here, this is the thing that the peers don't capture because of a lack of a line of sight. So this is the basic setup. Again, you can take the measures from the PCB and you can just as easily design your own according to your wants, needs and wishes. The parts that we realized probably wouldn't be changed a lot are the main board and the input serialization stack, which is why we try to make them as flexible as possible with the extra connectors that we aren't even using, but which may come in handy for for some other people, some other labs and uses. But with the power boards and with the cage-mounted sensor arrays, it's the idea was kind of to make the entire platform flexible enough. And you can this idea is represented in the fact that most of the important stuff is happening on these two boards, and these two boards are really simple. It's just translating one connector to other connectors. So it's just these pins going to these pins and making plus and minus common to these two pins. So it has plus minus, ground and data. And finally, for perhaps the most difficult part, the cables. Okay, so as for the cables, let's start off with the cables that connect the cage sensor arrays. Now, these cables will have this type of connector on one side, which plugs into the cage sensor array, and these connectors, these two, split on the other side. So 4 pins here, 4 pins here in total. This plugs in like so. Now you're probably familiar with these types of connectors. They're the ones you would find in phone lines and internet cables. They're basically zero insertion force, which means that you, unlike all of the other white little plugs sockets that we've soldered in, like these ones are friction lock, which means that you have to force the cable in there, and to pull it out you have to wiggle it left and right. For instance, like so. You align this, there's no mechanism, you just push it here, and then you kind of use your nails to grab this little skirted part, and you wiggle it left and right. You quickly get the hang of it after a few. Point is, these aren't really user-friendly. So they're used in places where you won't need to disconnect them and reconnect them a lot, which is the entire MIROSLAV array. Unlike them, this is one that you probably will be connecting and disconnecting often. So the most important problem with people using friction lock connectors is they generally don't grab the head and do this. They generally pull here, like so. And you can only do this a couple of times before this pulls out or breaks off. So you do kind of want a design which forces you and others to not yank this by the cable, and instead actually engage with the connector itself. And if there's zero insertion force, zero unplugging force, you don't have to apply any force. You just press on the pin and extract it. To plug it in, you just push it in, it clicks, and you know it fits in well. So this is why we went with this option. Okay. To make this type of cable, you can see the schematic on the schematic displayed right now. We try to make it intuitive by having the top part, having one part. If you turn the wire flat so it faces you, you will be staring at metal parts of both sides, and if you flip the cable, you will be staring at the little let's say spines or pins on each. So spines or pins on each. This is the stuff that determines which way you can insert them, and if you flip them, it looks like this. So you basically just need to make sure that the wires go in this way, as in the schematic. So for economy reasons, I actually got a roll of this flat cable that I just cut off and then split off the wires. You can see that I've been splitting it off. I use a pair of snips or scissors to, let's do it here, to cut. This is actually a bunch of wires. As you can see, it's a bunch of wires in one flat cable, which is nice because, for example, if you need a cable with 2 wires, you can just cut off 2 wires. For this, we said that we need 4. So you can see. Okay, so 1, 2, 3, 4. Just a nice slight little snip here, not to actually cut off and expose. We don't want to expose the copper. We just want to start it, and then you can peel it off with your fingers like so. Now, as this is for demonstration purposes, I will cut it off, and you will be able to better see how each wire connects to each one, because the cable that I showed you is actually one that we use in our experiments. It's pretty long, it's about 2 meters. So let's cut this here and get rid of this. Alright, so at the side of the little white connectors that go to the boards, that go to the power board and to the input serialization stack to get power to the boards, to the cage sensor arrays, and to get data of the cage sensor arrays. So they will obviously need to go to 2 different boards, one for power, one for transmitting data. So at the end you will want to split them like so, which is what you've seen here. We had the boards fairly close together, so this one we label it with a blue marker. This one is for power, and the unlabeled one went into the input board serialization. So to actually do this, this process is called crimping, and it's a bit more involved. Luckily, you can avoid this entire part by buying so-called pigtailed cables, which actually have you actually get a cable like this, and it's cut here and has exposed wires. So you have something like this, like a 2-pin pre-crimped connector with a cable that's exposed, and then you don't need to do the crimping, you just splice the wires to the other end, and that's it. However, we did the crimping actually, and once you get the hang of it, it's not that bad. So the main principle of how crimping works and how these connectors usually work. Let's show you. Okay, let's first take this out. These are the actual metal contacts. These are the metal contacts that will actually be, of course, in here. They're in here. And these are the metal contacts that will sit onto these pins in the connector. So it's basically turning a wire, just a bare piece of wire that you will see in a bit, into something that can fit onto these pins. Focus. Right. Because a wire, well, basically a wire and a pin, you can only wrap the wire around the pin. And this is actually like a, sort of like a small adapter. You'll see what I mean in a bit. Now, so if we have 4 contacts, or if we have 2 contacts per 1 connector, that means we have to crimp the metal contact to each of the little wires. So we need to split them apart. And then we need to strip off a bit of insulation. How much? Well, depends on this. You kind of develop a feeling for it. The way you crimp, and there's an excellent site about all of these different connectors. If you're like me and love to jump into a rabbit hole of a random obscure topic that's deeper than it may look initially, connectors are a good one, and this site in the description below is a great source. So there's a lot of good guides on how to crimp on the internet, and mostly the techniques will depend on the tool, on the connector itself, as well as the tool. You can get crimping tools on eBay, AliExpress, or whatever site for cheap that claim to be able to crimp many connectors, but as this connector fan guy shows while testing all of these different crimp tools, they're all kind of they're not really that good. To not be good, it means that they're, at worst, they're prone to breakage. At best, they're kind of bent a bit, and you will have a difficult time forcing it into forcing the connector into its shell, forcing the metal part into here. So what I use, and I only discovered the site later on, after I'd actually bought this, I use these crimping pliers. With these pliers, these are actually very, very thin, and you can nicely isolate what you're actually crimping. Let me show you what I mean by this. So here, here's a pair of tweezers to actually be able to point at stuff here. So there are 2 points in this little connector that you crimp. One is here. You can see the little like ladle here, so with the short wings, and the other one is here. This stuff is where the pin goes. So when this is actually part of the connector and it fits in, the pin will go to here, into here, and this will make this will make electrical contact of the pin in the connector with the wire that's crimped to here. Now this crimp point here is smaller because this is actually the one that will crimp the bare contacts in the wire, and this one, the distal one with the taller little flap, will be the one that's crimped onto the insulation for robustness and to actually maintain the connection so that the wire doesn't break off of this contact. So crimping is basically folding these two flaps onto the wire or the insulation. This is why this tool looks the way it does. You can hardly see it here, but you can see it a lot better here on the 1.9 millimeter one. So the bottom part, that's just a U, goes, this thing goes into here like so that the U handles the bottom part. The U handles the bottom part of the contact, just holds it in place, and this part you can see that it has a little notch. It's to actually, if you have the two little flaps, it's to twist the flaps onto the wire or twist them onto the insulation, depending on which one you're crimping. So at this point I will just try to go by feeling. We have these things literally cost less than a cent, the contacts, and you usually get a lot of the cable, which means that you can kind of try it out many times until you get the hang of it. Now I'm just stripping insulation. Usually I would do it in a batch. I would strip all of the insulation, and this is probably a good thing. I haven't done this in a while. Why is it a good thing? Because it means I haven't had many breakages of the cables, which in turn means that these are pretty nice and robust. So I will also be regaining the hang of it. And Anna actually did most of this. Second author on the paper, so she's the one with the magic hands. All right, and now you can see how it fits in. Just to let you see where the flaps are, position it like so that the smaller flaps are aligned with the metal part of the wire, and the long flaps are aligned with the insulation. If I recall correctly, I went with 1.4 millimeter crimp setting to crimp the wire, and generally you do crimp the contact first. Let me just restart the camera so you can see some of it better. Actually, this might be better. So what you can do is take it like so, put it onto here. Let me just make it focus a bit. So you align it with the base, press it down. So it's well aligned to crimp the part where the wire should go. And now I'm holding it in place. Now I take the wire, place it in, I push it in so I don't see the wire, which means it's well in there, being careful not to push in the insulation as well, and then I press, just get a better grip. If you press too much, you will detach it. If you don't press enough, it will pull out. And now you would basically do the pull out test. I think I might have pressed it. I haven't pressed it enough, but yep, there you go. The pull out test fails, and actually, since it's kind of bent to shape, maybe I can shove it back in. No, best not to even try it, because these things are cheap and I really don't want to risk having a bad connection. So we just try it again. Now I know I can use more force this time around. There's many ways you can do it. You can either put the wire into here first and then bring in the pliers, or you can grab this, put it into the jaws of the pliers. I think I can still use a bit more force. Why? Because the flaps haven't joined together, I think. We'll see. So for this I just literally clamp on the same thing again and press harder. You can see that it did, maybe you can see that it kind of shifted a bit to here, it bent a little bit. This is normal. You want to wiggle it out, or do what I did and press it on both sides. Don't it might kind of start to bend more if you just pull on one side, and that's that. Seems to be better. Pull out test again. Yeah, I cannot pull it out anymore. This is good. Okay, excellent. And now I will crimp the insulation, but this time I'll be using 1.6 instead of 1.4. Sorry about it. Another thing is that these tall flaps actually break the insulation and dig into the contacts as well, so they're providing electrical contact as well, and you end up with this, which is quite a nice crimp if I do say so myself. Okay, let's do it for the other three contacts. By the way, to remove this from the tape, you bend it back and forth repeatedly until it snaps off. Right. Next, we just need to put the shell. Now, just to make a parallel here, so these are 4 contacts, and making 2-pin contacts, 4-pin contacts, whatever, isn't actually all that different. You just make a sufficient number of contacts, and the only difference is actually the plastic shell, which groups them and organizes them. So we have to connect between boards and to connect the environmental passive infrared sensor. We use the 4 pins, and for the cable arrays and power we use the 2 pins. So this is the 4 pin, and we could jam this into here and get a 4 pin one as is. But right now I'm showing you how to build the connector for the cage sensor arrays. So this will be two of these. Right. Now comes the fun part, and if you crimp nicely, this will be fairly easy. Now, sometimes you may need to twist them a bit or kind of wrap them one around the other if your wires aren't of an equal length. It happens, like here. You can see that one wire was in the end, as it was crimped and pushed in, one wire ended up a little bit longer, and then you have these kind of crossed legs, let's say. But that's not that big of a deal. So on the back end, this is what we've been looking at while crimping mostly, right? So on the back end of these, you have this little pin, this little tongue, and this is what holds these metal contacts in place here by latching onto this little bit of plastic, and to actually disassemble them to get the pin back out, you would somehow raise this bit of plastic and pull out the crimped wire with the pin. This is how you would take the shell off. But the way to put it in is a lot easier. You just orient it like so that the little tongue is here. It's now pointing towards me. And then actually I will push in both at once, because if I push this one in, I will have to split the wire, kink this to be able to get it to fit. So immediately I will start pushing both in. Okay, now that we know the right side up, let's look at it from this side. Let me just refocus here. Right. Both are kind of started. Maybe a little bit, go in, and then you just kind of grab this until you see them here. Let's try to focus this. Maybe nice. You can see that they've latched. Now for these two, I'll show it to you from this perspective. Let's just first start them off. You can see that these are kind of rigid, a bit rigid wires, and I had to twist them a bit because I didn't really crimp both of them at exactly the right angle. This is not a problem, but yeah, just fiddle them around and get them in there. So I've started them Let's push them in. Okay, they're still not there yet. You can see how now this plastic part is lifted up. Let me just show you. Actually, this one is flush, horizontal. This one is lifted up as the little tongue is sliding in. Let me just find the focus, and now there we go. So right now you can really see the tongue on the left one, whereas the right one hasn't fully entered yet. And for example, this is why I'm telling you this, because this is an instance where the right one hasn't gone in yet fully, though it may look like it from afar. I could actually pull it out right now, but just let me show you how I know. Among other things, you can see that the plastic tab is raised. Here it's flat. And more importantly, I can't see the little tongue. Push it just a bit more, just farther. There it is. Now they're both flush, and even from the side you can see, this is a nice shot. You can see the two little tongues that have latched onto the shell. To remove the shell, as I said, you would raise off the tabs and pull out one by one. Okay, so now we have our power connector and our data connector. Okay, now we can look at the schematics, or we can just use well, a way to remember. If you're making many of these, it's I would just draw this, use the schematic that I've shown you, and label which one is which. Now at this point I label the power one, and power is the right hand is strong, or whatever, I don't know, it's just a silly thing that helped me remember. I use a marker and I color the entire side. This shell. Used to use a blue one, this is a black one, just to have one which is labeled. So this is power here. And now for the other side. Let's open this up. The other side needs to have this. Now, I find these really cool. They're also kind of doing crimping, but you have a different pair of pliers for these, and these are really quick and easy to do. Like cherry on the cake for the end of the video. You can see that these are protruding a bit from the bottom, and inside they have this little fork. So what will happen? This is also a part that will be crimped, this plastic little tab. So both of these parts, the plastic part and the metal part, the contacts will be pressed in. The plastic will press on the insulation to hold everything in place, and the metal part will slice into the wires to cut through the insulation and actually have a nice contact. So this is very cool because we're cutting out many steps here. We're cutting out the insulation stripping, the crimping of the contacts, each separately, and then putting on the shell. Here we're just putting on the shell. And now this is a thing that happens with this cable, where it's just a bit too thick to enter, and you can see inside that this is narrowing down a bit. So rather than just grab another, I don't know how many meters it was, couple of tens of meters roll of a different cable and shelf this cable, what we did was simply take a knife and strip the insulation on just this lateral part and at the far end, just to kind of make it here. You can see that we have been able to remove some of the material. This is completely fine because this part will be in the plastic shell and next to the lateral wall of the plastic shell, and basically don't have to worry about it coming into contact with anything else. It's not like we're stripping insulation between the wires, and they're pretty much all together as is. So let's see if I've stripped enough to push this in there. But you can see here that it fits nice and snug in place. Alright, and the wires are, you can see the wires here. It's really cool that this is transparent, and you can see that everything is in place. Now let's check. According to the schematic, this is a-okay. So we're looking at the metal, we're looking at the metal. We flip it, we're looking at the spine, and we're looking at the spine. This is a bit more difficult when this is 2 meters in length, so keep that in mind. And now the magic happens. Usually these pliers are a lot cheaper than the red ones, but you have to be sure to find those with this 4-pin RJ9, because this is, if I recall correctly, RJ 11 or 12, and this should be RJ45, which is Ethernet, phone, and this one, honestly, I'm not sure what or where. I think some phone lines, but at least not in Croatia. So let me just zoom out. These pliers latch, so they don't open up until you press them all the way. This ensures that you will always press the crimp all the way. And this part, this bit actually is kind of like a socket, a legit socket. So you put it in and it clicks like it would in a proper connector, but this time it's in the crimping pliers, and you just press on this enough that it opens up on its own. And let's see what we got. Pull it out. Pull out test with any connector, always a good idea. And you can see here, let me just refocus that. Let me just try to refocus that. I cannot because I'm still zoomed out. Okay. Now this is the connector. You can see that the nothing is protruding anymore, and this one wasn't protruding, but now it's pushed in. So going from the insulation, you can see that this plastic part is pressing on it and holding it firmly in place. So when you're moving this, the contacts aren't the thing moving, but it's crimped to the insulation for mechanical relief. And if you look a bit more closely, you can see that these little forks blades are far into the wires. And this actually has like four little crevices, like 4 little U's for each wire. As you push it in, this ensures that it doesn't slip around, and they're just the blade is just stuck through the insulation into the electrical contact. If you're unsure, you would use a continuity tester to check. And well, this is basically it. As for the other cables, like these ones, which connect as they do here, one moment. The double-sided tape still works, good tape. Okay, like so. These connectors which connect the boards together. Yeah, here's an example of one being very much too long. One wire in this cable, and then we just wrap it around. It works. So one thing to note is that I'll take this is the red one. This is the benefit of actually buying cables that are, for example, of 2 wires or of 4 wires, these flat cables. They are difficult to find with so few wires. But the cool thing is that the wire on one side, on the farmost side, is often red or some other color, sometimes blue or purple. And if you actually have a connector, it's floppy drives used to use these types of connectors, and parallelata before SATA, before M2 and NVMe and whatever. You would use these flat cables with a nice and wide connector that you would press on with pliers, and it worked just like the one you just saw. It had little blades that would puncture each wire. Now, the blades were, and because the blades needed to be very small, because this is quite small, they were in 2 rows. So this one would puncture this wire, this one, the one next to it, and then this one, the one next to it. Anyway, pretty cool. That's what these cables are actually for. But they're very good material for little bits and pieces of 2, 4 wire cables and whatever. One thing to note, when making cables like these ones that have this shell, this JST is the manufacturer, this JST shell on both ends, this one is good because you can trace the contact. So this cable, I mean, intuitively, at least for me, maybe I'm just a bit slow, intuitively I would probably crimp it so that when I look at the cable it looks like this, like I'm looking at electrical contacts. But when you actually think about it, this would be flipping the contacts. So if you look at it right now, if I'm looking at the metal part, so I see the metal contacts, the right one is red. If I take the other one, if I look at the metal contacts, the right one is red. If I put them like so and follow the wire through, it flips around because this works. And again, if in doubt, you can use a continuity tester. A continuity tester might be even easier to use. In this case, well, you can reach into here, but if not, just plug it in, and now you have bare pins that are very accessible with a multimeter or a continuity tester. You know, the one you put one wire on one end of the wire, a wire that you want to test, the other on the other, and then it beeps if there's continuity, which means your cable is nice and sane. Anyway, I don't know if these tips helped you. Might be silly, but all of this stuff was pretty much stuff that I had messed up at some point and learned the hard way. So, to summarize, we have the power board, which delivers power from the power outlet. And then we have, for the main part, the brains of the operation, we have a dedicated power connector, which plugs into, because this is 5 volts, it says here, right? Output 5 volts at 4 amps. You have the 5 volt in here. So in means I'm taking in 5 volts here. It's as if the board's talking. So 5 volt input is here. To connect the daughter board stack, you need to connect 2 things. Be sure not to confuse the interrupt with the 3.3 volt in. So this board is giving its 3.3 volt out, into the 3.3 volt input to the serialization stack, which stacks up the boards as well as its connections. The I2C connector is the 4-pin one, and there's the environmental sensors and the environment pair if you want it, as well as the plug for another board, again, if you want it. You can also additionally supply 3.3 volts to another board. Okay. If we add, now we have our entire setup. We add a cage, one cage, and we can use our new fancy little cable. We plug it into the cage. We've marked which one goes to power. This one plugs into here. And you'll probably want to space this out further. And you can plug it into the first input. So this says PHL0. This comes from I don't know, I think it was pin or it was the label in the datasheet. HL was high and low because initially we used the pairs not as redundancy but as high and low sensitivity based on the potentiometer, but given that they're variable enough, we just decided to set them all to high and use them as redundancy and cross correction. So this one will be PHL0. If you see in the Arduino code some reference to PH0, PL0 or PHL0, H and L now just refers to either of these two wires. Doesn't really matter which one is H, which one is L, except for if you're trying to redesign this PCB, then you'll see how it's routed. You plug it in, so you can see the cage sensor array is powered with 5 volts directly. It's communicating its stuff to the 3.3 volt input serialization stack, which is powered with 3.3 volts from the main board and is transmitting all of the stuff all of the stuff from all of these pins. We adjust these 4 wires to the main board, which reads the environmental sensors and transmits it out via this radio. This squiggly part is actually the antenna. All right, one last thing. You can use this in another configuration, and that's without virtually anything connected to the main board. You can just use the main board as an environmental monitor. You can hook up the environmental peer for entrance monitoring, and you can use the temperature and humidity and light sensors to monitor temperature and humidity and illumination in the habitat. Maybe you could theoretically even mount this on top of a cage, if that makes sense at all, to monitor data from closer to each individual cage. I'm not sure if this makes sense with an open top one, but either way. Or you could move these two out onto a separate board, which would connect to the I2C bus here. It's important to note that this I2C bus is separate from this one for the peers to avoid address clashing. So you could actually use, if you're not using peer, you have another I2C port here. So you can actually just remove peer monitoring and use this as an environmental sensor monitor. You can also use the power supply as we did with the 5 volts in, but you can also just skip this entirely and grab an old cell phone charger and plug the USB cable into here and power it like so. The USB cable would mess with your illumination sensor, which is bad, and that's why the redesign that I mentioned at the beginning, the version 0.5, whereas this one is 0.4, which places out the sensors here, spaces them out a bit, and leaves you a free USB port. Right, that's it. So if you made it to the end of all of these ramblings and experiences, thanks for watching, and props for persistency. I hope this video had some good tips for you and will be of help, but if not, feel free to send me an email. You will find it. I have a GitHub repository, I have a Blue Sky account, I have an email, which is my first and last name at gmail.com, probably in some papers as well. So feel free to send me or any one of the authors an email, and we'll try our best to respond to you if you have any technical queries, any experimental queries, if you need help with the designs, if you need help with any part of the video, or if you just want a MIROSLAV device sent out to you to try it out. We're always happy to share our work and our these little devices that we build. So here's hoping to hear from some of you. Thanks. Bye bye.